I will begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for this class and just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So have no fear, I have not graded anything. So whatever happened, happened. We'll see, yeah. Hopefully I'll have it back to you Friday if everything goes as I hope. Do you guys have any questions about anything before I get into it? What I was going to do at the moment is just talk more about the Jordan forms and like what we can say about it. And there is a most unfortunate typo in the notes I should mention. On page 145, I have, well, I mean, there's various ways to look at it. But let me just, so here's just some, how to say, some thoughts on how to calculate, generalized eigenvectors. And I won't give you a full, I'm not going to give you a full algorithm for it, all right? But I do want to say some sort of like obvious things here. So like, here's a generic observation. The kernel of S is naturally a subspace of the kernel of S squared. Let us just pause and calmly think of this, yes. So why is this true? What does it mean to be in the kernel of S? So if X is in here, right? That means that S of X is equal to 0, right? So therefore S of X, also known as S squared of X, is equal to 0, because S of 0 is 0, because S is a linear transformation in this discussion. So therefore, the kernel of S is a subset of the kernel of S squared, but we also know that kernels are subspaces, right? So because of the general property that kernel's a subspace, we get the advertised inclusion of the kernel inside the kernel of S squared, right? And this goes on, right? You can keep doing this. This is a subspace of the kernel of S cubed, right? We could be here all day, right? Right, and so forth. Yeah. What has to happen here, by the way, if we're talking about, and I do want to talk about S, a linear transformation on a finite dimensional vector space, guys. Tell me what has to happen here for this kernel. I mean, at some point, this sequence has to do what? It has to stop, right? There has to be like, it can't just keep getting bigger and bigger and bigger, right? This all, no matter how far you go, has to fit inside what? V, right? And so if these were like proper inclusions, right? It would force it to be constant after a bit. Yeah.
For certain S's, does it stop at a constant value rather than go all the way to B?
Yeah, it could. It could, because like all right, so like let's see here. Example. If we look at A equal to, let's say the 4 Jordan block of 3, direct sum with like the 2 Jordan block of 1, yeah, that should be enough, right? Right. And then we like think about t is equal to left multiplication by a, all right? Then what that's going to mean is that we've got E1, E2, E3, E4, a 4-chain with eigenvalue 3, and E5 and E6 is a 2-chain with eigenvalue 1, right? And so if I looked at the kernel of, let's say, t minus 3, that's a subspace of the kernel of t minus 3 squared, which is a subspace of the kernel of t minus 3 cubed, which is a subspace of the kernel of t minus 3 to the 4th, all right? What are these spaces, though? So this right here is, of course, what we call the eigenspace, right? Now, for this matrix, the only eigenvector is E1 for eigenvalue 3. So this would just be the span of E1. Now, t minus 3 squared, well, E2 is a generalized eigenvector of order 2. So in this guy, you got the span of E1 and E2. Here, this one, span of E1, E2, E3. Because 1, 2, 3 is actually a 3-chain, truthfully. I mean, you can always take a k-chain and stop it before it gets to the end, and it's a subchain of whatever length you're at. You know, like if I have a 4-chain, I take the first 3, it forms a 3-chain. And then when I get to the 4th one, it's also, I mean, this is, of course, the span of E1, E2, E3, E4, right? And then past that, nothing new is added, right? So this would just be equal to the kernel of t minus 3 to the j for j equals to like 5, 6, 7, forever and ever, right? So once it gets to 4, it just stays there. And it never picks up, right? It never picks up the eigenvectors that are paired to the other block. See, on the flip side, the kernel of t minus I is a subspace of the kernel of t minus I squared, right? And this guy, span of E5. This one, span of E5 and E6, right? And past that, there's nothing more. So in fact, in terms of the language I introduced last time, in this example, this is k lambda equals to 1, and this is the generalized eigenspace of lambda equals to 3. And in my current context, like R6 would be, k lambda equals to 3, direct sum k lambda equal to 1 for this example. So, of course, if we have an explicit matrix, we can have this conversation, right? But what's more interesting is if I give you like partial information, and you have to try to like work backwards and see if you can think about what's the deal. So like here's an example that's kind of like that. So here, I tell you have t, a linear transformation from v to v, with the dimension of the kernel of t minus 3 equals to 2. The dimension of the kernel of t minus 3 squared equals to 4. The dimension of the kernel of t minus 3 cubed equal to 5. The dimension of the kernel of t minus 3 to the 4th power equal to 6. The dimension of the kernel of t minus 3 to the 5th power equal to 6. All right. What can you extrapolate from this information about the linear transformation? Like, what can you say about the eigenspaces with eigenvalue 3 in this context? You guys know? So the theorem I shared with you guys last time is that we can always build as long as the characteristic polynomial, of course, is split, we can build a Jordan basis by taking a union of k-chains. Union of k-chains for the linear transformation, right? The question is, what kind of chains can I see from the data I have here? Like, think about how the chains work. Every chain has an eigenvector at its start, right? And you work up to the largest one. So, like, this right here, this means that I got two total chains, right? So maybe we start the first one with v1 and start the second one with w1 for my eigenvectors, right? And then I've got 4 here. What's that mean? Remember, this includes not just itself, but also the subspace of eigenvectors. The question is, what's new here? 2 new things, right? So that means that both of the chains are continuing. So there's also like a V2 and a W2. That's what I see from here. All right? So, like schematically. Now, the way that Inzel, Spence, and Freeberg does this, they introduce these things called dot diagrams in Chapter 7 to like make this systematic. I don't teach those in here, but I'm just trying to show you basically the idea of it. All right, so I get 5. What's that mean for the next level? That means that if both of the chains continued, we'd have 6 there, right? But we don't. So just one of the chains continued. Which one do you want to make continue? The V or the W? It's your choice. V? All right. So there is a generalized eigenvector of order 3. There's just one up to linear independence right there. That's from this 5. Okay? And then the 6 means that, there's one more generalized eigenvector that's bigger in terms of, height, if you will, position on the chain. So there must be a V4, right, in order to get that. We can't continue this one. You can't jump past 3. The chains always come with generalized eigenvectors from order 1, 2, 3, all the way up to the max. You can't just like go back into a chain and adjoin a higher one without getting the in-between ones. They're always a package deal. And then, right here, nothing new, right? End of the story. So what this all means is that k of lambda equals to 3 is like the span of v1, v2, v3, v4, w1, w2. And if I was to call this the basis beta, right, then if that's all there was, if the dimension of v happened to be, 6, right, then the matrix of T with respect to these chains would be what? We've got, first of all, a 4 chain with eigenvalue 3, which means I do 3, 3, 3, 3, 1's on the superdiagonal. And then I've got a 2 chain down here, so I get another 3, 0, 1, 3 like that. And that would be the Jordan form of the linear transformation that follows from these particular kernel dimensions that I gave you. Yeah? But, the error, the typo I was mentioning in the notes is I should say the dimension of the kernel of t minus lambda to the power j has to be less than the dimension of the kernel of t minus lambda to the, I think I was thinking about it, and I think it should be j minus 1 instead of j plus 1. Oh, excuse me, I have to say, words matter here. Before this I have, we cannot have this. You can't have the dimension of a smaller power being strictly less than the dimension of, I mean, you can't have the, if I'm decreasing the power, we have to be like, we can't be going to a larger space, right? This is opposite the thing I started class with. And in the notes I have a j plus 1 instead of a j minus 1 there, which I don't think is correct, all right? That's on page 145, there's a typo. All right, so I have a few more examples on page 146. I'd encourage you to read those, to think about them, all right? I won't go over all of them here. I just wanted to go over one carefully. The other thing I should mention for you guys before I forget is we also like to think about, we talked about the characteristic polynomial, right? But there's also something called the minimal polynomial. So given t, a linear transformation from v to v, where the dimension over the field f of v is equal to n, we know that the characteristic polynomial of t of x, if you like, I usually call it p sub t of x, right, is what? Degree, what's the degree of the characteristic polynomial? I heard an n? Very good. And our definition of it was what? Pt of x was what? Determinant of t minus x, wasn't it? And so if this is split, how does this work out? This works out to minus 1 to the n times x minus lambda 1 to the, I think we said a1, x minus lambda 2 to the a2, right? X minus lambda, however many you have, let's say s, to the as, right? This is the, split condition. Here we're assuming lambda 1 through lambda s are in the field, right? So some things you should notice here, that I haven't worked out yet, but just what happens if we look at the constant term? What is it? If you multiply this out, what do you have? You have minus 1 to the n, right? I mean, specifically, it's p sub t of 0, right? That's how you get the constant term. So I have minus 1 to the n times what? Minus lambda 1 to the a1, and so forth and so on, yeah? Minus lambda 2 to the a2 power, and so forth and so on. So can you guys simplify that? How many minus 1s do we have? Minus 1 to the n times minus 1 to the what? a1 plus a2 plus da-da-da plus as, right? And then the product of the eigenvalues. How's that work out? What is a1 plus a2 plus a3 da-da-da plus a sub s? What's that have to be equal to? If we believe Avery and her claim. Was it you, Avery? Or was you, Sammy? I forgot who said it. What's that? What? Who? What? Oh, n? Yes, n. So what is minus 1 to the n? You said it? Okay. You guys sound the same to me when I'm just looking at the board. So this is also minus 1 to the n, which means we have what? 1. So this is simply the product of the eigenvalues, right? That's kind of important to know. It's not particularly surprising if you think about what the eigenvalues are as they relate to the characteristic polynomial, but it's kind of nice to know. Now, we had the Cayley-Hamilton theorem. What did that say? Remember, we had that P sub t of big T is equal to 0, right? So that was helpful, I suppose. But getting to the point here, our definition, though, the minimal polynomial for T is the monic polynomial m sub t of x in, of course, fx of least degree for which m sub t of t is equal to 0. So if you look at the Cayley-Hamilton theorem and the definition of the minimal polynomial, what's that mean? Put these two ideas together. We must have that m sub t of x has to do what? It has to divide p sub t of x, right? Like, and it's more than that. You can prove that they have to share the same factors, actually. So like this is, by the way, theorem m sub t of x and p sub t of x share same zeros. Not necessarily the same multiplicity, though. Okay? So it could be that, I can't spell. Anyway, the multiplicity doesn't have to be the same, all right? So like, just specifically, just to give you an example, for my example 2, you can work out, of course, the characteristic polynomial is what? It's kind of boring. It's just, x minus 3 to the 6th power, right? That's actually the characteristic polynomial there. What's the minimal polynomial for my example 2? I mean, generally speaking, this takes like calculation. You have to think about it, right? But you can work it out that m sub t of x for this one is x minus 3 to the 4th. Because basically the thing is, if you look at the matrix of T, beta beta minus 3i, all right, then what you've got is this 0, 1. Well, let me just get to the point. You've got n sub 4 up here, the nilpotent matrix of order 4, and you've got the nilpotent matrix of order 2 down here, all right? And what happens as you square that, the first square makes the n sub 2 squared goes to 0, right? But n sub 4 squared is not 0, all right? N sub 4 cubed is not 0, but n sub 4 to the 4th is 0, right? You have to take this super diagonal 1, 1, 1 and power it not once, not twice, not thrice, but 4 times before it goes away. And at that point, it's gone. And this was already gone at order 2. So the lowest order polynomial, which the lowest order power of t minus 3i, which gives you the 0 matrix, is 4. And working backwards, that shows me that, actually the minimal polynomial likewise is x minus 3 to the 4th. So anyway, I think you have like a token homework problem about this, so I just wanted to say a word or two about it. Yeah. Anyway, you guys can come ask me more questions about this if you want. But I'm going to move on and start to discuss the complexification. All right. So the weakness in what we're currently doing, right, is that it only works if the characteristic polynomial is split, right? And we are interested in real problems, and many of those real problems have a characteristic polynomial which is not split because you need complex numbers to split it, right? But if we can take these real problems and we can turn them into complex problems, then we can use the magic of complex polynomial algebra to be sure that we have a solution. And that's basically the driving idea behind what I'm about to do. That's why it's interesting. But it's also interesting independent of this discussion, independent of the problem of finding the Jordan form, right? It's still just an interesting question of like, if you have a real vector space, can you construct a corresponding complex vector space, and how is that done? All right. So this is what I call the complexification. And what we're going to do is we're going to start with, we're given the vector space over the reals. All right? And I'm going to define V sub c to be equal to x comma y such that x and y are in V. What is that, by the way? I mean, as a point set, what am I doing? This is nothing more than like V cross V, right? It's the Cartesian product of V and V. So we already know that that forms a real vector space, right? If you think back to what we did before, the Cartesian product of vector spaces is again a vector space of the same type. But I'm going to do something a little bit different here. I'm going to actually show you that V sub c can be viewed as a complex vector space. So what's the scalar multiplication is the question. So is a complex vector space provided we define, and the one is a total snooze fest. If I have x comma y plus, I'll say x1, y1 plus x2, y2, we're going to define addition how? The same way we always do for the Cartesian product, x1 plus x2, y1 plus y2. All right, so there you go. That's how we define addition. I invite you to check that that's associative, commutative, and meets all of our usual terms and conditions. All right, but the next one is tricky. And we're going to say for a plus ib times x comma y, all right, our definition of scalar multiplication is going to be ax minus by, comma, bx plus ay for all a plus ib in C. And of course, my custom here is that a and b are real, all right? So when I write a plus ib, let it be understood, for the sake of me not saying 1,000 times that a and b are real, when we write a plus ib, it is our default assumption to assume that a and b are real numbers, all right? If in doubt, ask me, though. But there you go. This is our definition of complex scalar multiplication. I think it's fairly evident that this definition, right, it definitely gives us, is this an element of V cross V? That's pretty clear, isn't it? Because we're looking at scalar multiples of real vectors inside a vector space, so they're once more in the vector space again, right? Since V is a vector space, it's clear that this and that are once more in the vector space, so it's closed. What other axioms do we need for it to work? How about 1? How does 1 have to work for scalar multiplication? Remember how it has to work? 1 plus, what is 1? 1 plus I times 0, right? That's 1. So how does that work? A is 1, so 1 times x minus what? 0 times y, comma, 0 times x, right? Plus A is 1, 1 times y. Oh, look at that, xy. That's good, because that's one of the axioms we need for scalar multiplication to work. We need that 1 times a vector gives me back the vector, right? That's required. What's the other axioms we need for the scalar multiplication to work? Distributivity. That is true. Oh, that seems unpleasant, but let's do it. Actually, maybe that's your homework. That should have been a homework. Is it a homework? Or no, it should have been a homework. Rats. Well, I'm going to have to erase something. Now, actually, before I forget, so yeah, we can check that, in fact, this does satisfy the axioms of a scalar multiplication, right? And this is interesting because we started with a real vector space, right? But now, I'm telling you, we have a complex vector space, right? Because we have defined how to multiply by a complex number in this new vector space. Now, one thing I should mention before I get away from this is what's 0 plus I, plus, I times 1, how's that work out? So we've got, 0 times x minus 1 times y, comma, 1 times x plus 0 times y, right? The mirror story to my multiplication by 1, multiplication by I, actually gives me minus y, comma x, right? That's how that works. All right, so I'm going to resist the urge to prove distributivity because it's not that interesting, and it will eat the rest of my class time. But it would be a good exercise for you guys to check the other axioms, all right? But can you guys see, what's a better notation than what we're doing here? Here's the thing. We can do better. What if we write x comma y is equal to x plus iy? But we're talking about abstract vectors, right? In that notation, how does the scalar multiplication work? We have a plus ib times x plus iy. What's it equal to? Ax minus by, right? Plus I times what? Bx plus ay, right? Yep.
Did we need an additional definition for when we multiply? Oh, I got it.
Cool. So the there are two special subspaces to think about here, right? If we let W1 equal to basically things of the form, say, x comma 0, x and x, right? X and v, and W2 equal to 0 comma y, such that y and v, right? Then those are, I gotta be careful here. I say that those are subspaces. I think that's just wrong. I think the notes are just wrong here. I claim that these are subspaces of the complexification. I just don't think that's true. They're real subspaces. If we looked at so the complexification is a complex vector space, right? Every complex vector space can also be looked at as a real vector space because you could just restrict the complex multiplication to real multiplication, right? So with respect to the real multiplication, these are subspaces. But these are not subspaces with respect to the complex multiplication, because if you take something in there and you multiply it by I, you're not in there anymore, right? Like W1 and W2, these are real subspaces. Let me just say it out loud. These right here, these are real subspaces of, let's say, V sub C viewed as a real vector space. But W1 and W2 are certainly not subspaces of the complexification looked at as a complex vector space. Why? Because if I have, I times x0, I get 0 minus x, right? And if I have I times 0y, I get minus y. I just get 0x, my bad. I get y0, all right? Which, of course, is not an element of W1, and this is not an element of W2, right? So neither W1 nor W2 are closed under complex multiplication, certainly not. But those have names. What are they? Like W1 is what I would usually call the real part of the complex vector space. And I would probably call W2 the imaginary part of this complex vector space. And I might even write the following. I might even say, well, really, the complexification of V is really V1 direct sum. Well, fine, it's W1 internal direct sum W2. Now this is over the reals, to be clear. Actually, I think I'm sorry, I have gotten sucked into my own notes at the moment. This is not really where I should be. We should move on. Let me finish it. So this, though, we could also denote as V direct sum IV. Like IV is a natural notation for W2 because it's just I times a real vector. Right? That's what those vectors are if you can understand the notation. All right. Sorry to delude you. I mean, this is just an unnecessary. Do you see why those are internal direct sums? Like, if I add these two spaces together, do I get everything in the Cartesian product? I do, right? Because if you add this and that, you get x comma y, which is an arbitrary element of V sub C, right? In the intersection of W1 and W2, is it clear to be 0? It's pretty clear, right? So we have this internal direct sum. They are independent subspaces. In fact, they're the real and the imaginary vectors inside the complexification. Now, there are, let me just give you kind of a roadmap here. To find the complexification of a vector space V over R, we simply consider V over C. I mean, I haven't proved this, but basically this is a claim. Like, let's see here. What's that? Oh, your water. That was your water bottle? Yeah, interesting. So, where was I? Example, what, 3? I can't remember. Am I on 3? Nah. Okay, 3. So here's a couple real easy examples. If I have the reals, if I have Rn, if I have Rn by n, these are all real vector spaces, all right? The complexification of V is just C. The complexification of Rn is naturally viewed as Cn. The complexification of m by n is naturally Cm by n. So what I'm saying is that you can look at C as the pairs x comma y, right? Right? Which we can look at as x plus iy, that's our notation, right? That is what we do. This is the complex number system, yes? And look at my definition of multiplication. It's exactly that. The usual definition of multiplication of complex numbers. So the idea of this construction is to abstract that idea to an arbitrary vector space. All right? Now, the big theorem here, big theorem is maybe too much. That might be a little bit of a little bit of a stretch. But it's interesting to try to find a basis for the complexification. And yes?
So you can complexify the vector space over R, right?
Right.
What if we consider C as a real vector space and try to complexify that?
If you tried to complexify C, you could do that, but you'd have to do it thinking of C as a real vector space. So it would just be R4 with a funky multiplication, I guess. I mean, we could do that, yeah. But here's a proposition that's going to be important to us like next time. We're going to need to remember this one. Suppose V over R has basis beta equals to V1, V2, Vn. All right? Then, get this. Beta is likewise basis for the complexification of V. Do you understand the difference in what I'm saying? I'm saying to start with, the real linear combinations of this set fill out the real vector space, V. I'm then saying that that same set of vectors viewed as naturally a subset in the complex. So what I mean by, this begs a question. Hold on, you might be like, hold on a second here. So first of all, understand that when I say beta is likewise a basis for C, I'm identifying, to be clear, I'm identifying beta with what? With beta unioned with 0. Right? In other words, I'm identifying beta with like V1, comma 0, V2, comma 0, right? Vn, comma 0, which looks much less intimidating if you look at it as like V1 plus I times 0, or V2 plus I times 0, right? You might not even notice it if I use that other notation. So that's the danger of the other notation, is it makes you take certain things for granted. The plus I notation does. The comma notation is just in your face what you're dealing with. But, so, like if this was Math 200 and you just identified beta with beta, I'd like take off all your points, right? Because like the whole point is to make a distinction in the problem in Math 200 I'm thinking about between like points and points paired with other points, right? But we want to identify beta with this. All right. Do you see then that this is a subset of the complexification? Do you agree, right? Because it's, they're pairs of vectors. Okay, great. So let x comma y be an element of V sub c, right? Then x and y are both elements of V, which is the span of beta, right? Hence, there exists x sub I and maybe I should use j, x sub j and y sub j in the reals, such that what? Such that x is the sum I equals 1 to n of like x sub I, v sub I, and likewise for y, right? I meant j equals 1. I'm trying to use j because the I is the imaginary unit here, All right, then what? If we have x comma y is equal to what? Well, it's x comma 0 plus 0 comma y, isn't it? And so, of course, I can, sorry, my energy is waning. This is, phooey. I need to. All right, x sub j, and I got v sub j comma 0. Sorry, I seem to have skipped a step here. Plus the sum j equals 1 to n of like y sub j times 0 comma v sub j, right? All right. In my current notation, you guys got to help me out. How do I move this Vj over here? Let me remind you guys how this works, right? We have I times x comma, I'm using x and y here, but no relation, right? I times xy is what? It's minus y, comma x, right? So if I have, well, how about this? Minus I squared is 1, right? So if I have minus I squared times 0 comma Vj, that's equal to what? Minus I times what? Minus I times I, 0 Vj, but then of course I can do what? I've got minus I times, well, minus Vj comma 0, right? And then pull the minus out, and we just have I times Vj comma 0. So here's an identity. 0 comma Vj is equal to that. Yeah. Now this is way, way less impressive if you use the other notation. Because in the other notation, this just looks like I times Vj plus 0 times I is equal to 0 plus I times Vj, which hardly seems surprising. But nevertheless, that's what we have to deal with here. To move that to the other side then, we have the sum j equals 1 to n of x sub j v sub j comma 0 plus the sum j equals 1 to n of y sub j times I v sub j comma 0. But then we can combine the sums, you see, and we've got the sum j equals 1 to n of x sub j plus I times y sub j, ooh, times vj comma 0, which tells me that x comma y is an element of the span of vj comma 0 such that j is equals to 1, 2, da, 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 n, right? In other words, this is, of course, the span of beta as we're viewing beta, identifying beta as a set of complex vectors. Therefore, beta is a spanning set for the complexification. Notice the coefficients here are complex now, yeah? These are complex coefficients. Previously, they were real spans for x and y, but that goes to a complex span for x comma y. Now this proof looks way, way easier if you just use the notation, like the not comma notation, the x plus iy notation. This proof becomes like much, much easier. But I wanted to suffer through the comma notation to help you see like what's involved with really thinking through it. What's left? To show it's a basis, we need what? Linear independence, right? So if you take this arbitrary linear combination and put it equal to 0, right? Let's think through this. Here's an arbitrary linear combination. I'm putting it equal to 0. So these are my C1s, my C sub j's, right? Linear combination equal to 0. Does that force all the C sub j's to be 0? Well, this calculation reverses, right? So this just goes back to, x, the sum of the x and the y piece, right? The x sub j, v sub j, and the y sub j, v sub j here and here. And that's equal to 0, comma 0. Therefore, all the x's are 0 and all the y's are 0 using linear independence, the real linear independence of the basis, right? And so, yes, we get that this is a basis for the complexification. Yeah. Anyway, sorry, I should have spent less time on my my silly Jordan form stuff, but anyway, we're not done with the complexification. We'll do more next time, but I just wanted to get started today. Thanks, guys.